Hello everybody, welcome to today's video. We'll get straight into it here. We're going to be looking at logarithmic functions and their graphs today. So we'll start by looking at the definition and the relationship to exponential functions. There is a very direct relationship there. We'll talk about converting between the two forms, the exponential form and the logarithmic forms. We'll talk about two special or common sorts of logarithms, the common log and the natural log. The common log having a base of 10 and the natural log having a base of e. We'll talk about shifting some logarithmic functions around on the coordinates a little bit, and then we'll talk about the domain, range, and vertical asymptotes as we go along the way. So we'll start with the definition here and kind of like a little pre-definition. I think that logarithms often get kind of just stuffed at the end of an algebra course or something, and students don't really get a lot of time to sit and think about them and what they are. As soon as I just figured out that what does a log function do, it gives you an exponent, it made things a lot clearer to me about what was happening with logs. So that's what I have written here first, is that the function log base b of x tells us what power of b will give us x. X to what power, or I'm sorry, b to what power will give us x. There is a new log function for every positive value of b, as long as b is not equal to 1. So here's the kind of definition here, the full definition. If b is positive, so bigger than 1, and not equal to 0, then the logarithmic function with base b is defined with this relationship, and it's showing exactly what I was saying. If log base b of x is giving us y, that's telling us that we need to put y as a power on b in order to get x the other side. So this is the inverse function. In fact, I have that written below here, that the log and the exponential are inverse functions of one another. So switching back and forth between these two forms can be a super beneficial thing to us, especially later on as we try and solve some of these logarithmic functions, or logarithmic equations and exponential equations. A lot of these words are a mouthful. So note that, like I just said, log functions and exponential functions are inverse functions. So that is that if f of x is log base b of x, then its inverse function is b to the x. One is the log function is finding the exponent that is given on that exponential function there. So if we want to talk about finding the domain and the range of the log function, well, it can be helpful to maybe look at the domain and the range of exponential functions, since we already know what those are. So just drawing a quick little graph of the exponential function here, just some random b to the x. We see that the domain is plug anything in. There's no restrictions on the domain. So from negative infinity to positive infinity, there's the domain of the exponential function. And remember that the domain of one function is the range of its inverse. So what I'm saying is we can send this domain and make that the range of its inverse, which is the log base b. If I can draw my infinities, there we go. Similarly, the range of the exponential function over here is just the positive value. So this is getting asymptotically close to 0. It never will reach 0. So the range here is going from 0 to positive infinity. So just like before, the range of one function becomes the domain of its inverse. So that means that the domain here is 0 to positive infinity. So what we're seeing here is that the only numbers that we're allowed to plug into the log base b function are positive numbers. So not even 0 works here. So yeah, there we go. And then if I do a quick little sketch of what the log function looks like, it's going to look something like that. So we can see there that we have a domain going from 0 to positive infinity and a range of all real numbers. All right, next we will take a look at some examples here using the definition of the log that we just saw. Like I like to try and think of these things as intuitively as possible. And so when I see evaluate here for this first one, log base 5 of 25, what this is asking is to find the exponent, find the power you would have to put on 5 to get 25. So you might be able to think of what that is already. But what this is telling us is, what power do I need to put on 5 to get 25? And here what we have done is, well, if I had set this equal to x to start with, so let me back up and say, let's just set this equal to x. if I now put that in that logarithmic form, what we have here is 5 to the x equals 25. So either way we look at it here, if we're just trying to think intuitively about what the log function is doing, or if we want to just put it in that other form, we're able to now think, okay, what would that have to be? And this would tell us that x would have to be 2. Later on, we'll get some more formal ways to kind of think about this, where we can use some equalities and some nice things to specifically solve for x here. But right now, we're just kind of using things that we know. So similarly here, what number 2 is asking is, okay, the log base 3 of 81 is saying, what power do I need to put on 3? What do I need to raise 3 to get 81? So kind of intuitively here, or if I want to set this equal to x, this is saying, what power do I need to put on 3 in order to get 81? And you can think about your powers of 3, maybe just start multiplying them together. 3 times 3 is 9, times 3 is 27, times 3 is 81. So there we get that x should be equal to 4. Moving on here to number 3. We've got log base 16 of 4, and here's where things can get a little tricky if you're not paying close attention. So we can do just like what we were doing before. We can set this equal to x, but what this is saying is, what power do I need to put on 16 to get 4? So what power do I need to put on 16 in order to get 4? So this is now getting a little trickier, but I think that we'll see that 16 to the 1/2 is equal to 4. So in this case, x must be equal to 1/2. So again, if you have x to the 1/2, that's the same as the square root of x. So that's the property that we're using there for those rational exponents. And then finally, we've got log base 6 of 1 over 36. So we can do kind of like what we were doing before. We can just set that equal to some variable x. We don't know what something is. We can always just give it some variable name and use it from there. And so this is saying, what power do I need to raise 6 by to get 1 over 36? So, you know, we might be thinking, okay, to get 36, we would square 6, and then we need to take a reciprocal. So we'll get the negative exponent out of that. So we know that 6 to the negative 2 is equal to 1 over 36. So this will tell us that x is equal to negative 2. So here we were able to evaluate all of these by just setting them equal to a variable, putting them in the other form, and then being able to use things that we know to solve. Here we will use the definition to solve for specific cases of x here, being in some different places. Before we were setting these equal to x and solving. Now x is embedded in the problem here. So we're trying to solve for the argument of the function here in this first one. So we're just going to put it in the other form. What this is saying is I need to put 1/2 as a power on 25 to figure out what x is. So this is putting it in the other form. Sometimes people like to think about this loop as well. I'm just going back a little bit. And this can be a helpful visual thing. For a long time before I understood what logs were doing, is I just thought, okay, this is the base of the log, so it's also the base of the exponent, and then we make kind of this circle, and it says that 25 to the 1/2 is equal to x. So just kind of a visual way to think about this too. So now I can just simplify this. 25 to the 1/2, this says x to the square root of 25, or x equals 5. And then the last one over here, we'll do the same sort of thing, where the base of the log will be the base of my exponent, my exponential function, and then I can think about making this kind of visual loop here. This will say x squared is equal to, let me move it down a little bit now. Whoops, that's not the eraser. This says x squared equals 9 over 4. So if we take the square root of both sides now, we will technically get a plus and minus there. So we're going to get x equals plus or minus 3 over 2. But since we were solving for the base of a logarithm, we know that the base of logarithms, from the definition we had before, have to be positive. The base of a logarithm is always positive. So we can get rid of the negative version, and we've just got x equals 3/2, and that is the base of this exponential, or of this logarithm rather. All right, we'll take a second and mention the common log and the natural log. There is a new log function for every single base that's a positive number, except for 1. So maybe first we should talk about 1. If we did have b, I'm sorry, not b, but 1 to the x, then that's not very interesting. We just get 1 every single time. So that's the reason that we don't have 1 as a base, and it needs to be positive. So just some specific ones that happen a lot. The first one is the common logarithm, and this has a base of 10. So, normally we might write it like that, but we often will see it denoted with the 10 not showing. So we'll often leave off numbers if they're common, like square roots. We don't always write the 2. We don't always put all fractions over 1. Here we don't need to write the 10, and if we don't, we're assuming that it's the common log. And then same thing with the natural log. This will be your best friend when you get to calculus. You will see a lot of the natural log. And it is a logarithm with base e. And it happens so frequently that it also gets its own notation with the ln of x. So we'll just look at a couple examples here, just kind of maybe rewriting them or thinking about what we need to do. But here we have just log with no indicated base of 100, but what this is implicitly saying is this is log base 10 of 100, which is asking, okay, hey, what do I need to raise 10 to get 100? 10 to what power is 100? And hopefully it's clear that x should be 2 in this case, since 10 squared is 100. So there's that one. This other one doesn't want us to evaluate, but it wants us to just write it in that logarithmic form. Going this direction I think is sometimes a little bit trickier, but I remember that the base of the exponential is the base of my exponent, so I know I'm going to be writing log base e of something, and I know that the log function is always finding the exponent, and the exponent is the is the x value up here, so that must mean that this is equal to x. And then by process of elimination, that 9 must go as the argument of the function. And now I can think, okay, yeah, this says e to the x equals 9. Okay, everything's in the right spot. I feel good about this. And then we can just rewrite this with the proper, or the more common notation, which is the natural log of 9 is equal to x. So here we have written that in logarithmic form, and we are good to go. So next, we'll take a look at some different shapes of graphs here. So I've just got the exponential function compared to its inverse logarithmic function here, just so we can compare the different rates of growth between the two functions here. The two groups of functions, I guess I should say. We'll start by looking at the function 2 to the x. So these are all exponential functions. They're all going to grow very quickly as soon as they get not too far into their positive domain here. But we see that as the base gets bigger, the function grows more quickly. So 5 to the x is growing more quickly than 2 to the x, and 10 to the x is growing even more quickly than 5 to the x. So remember that for every increase of 1 in the domain, for 2 to the x it's doubling. For 5 to the x it's being increased multiplied by 5. For 10 to the x, it's being multiplied by 10. So for every 1 unit you move over, your output gets multiplied by 10. So the log function is doing the inverse of what the exponential function is doing. So if the exponential function is growing faster and faster and faster, that means that the inverse, the log function, will be going slower compared to the other counterparts here. So what I'm saying is, let me go back to my blue, the graph of 2 to the x grows the slowest over here, but its inverse, log base 2 of the x, is growing the quickest of the three. Because in order for these to undo each other, the faster one is going, the slower the other needs to go, and vice versa, in order to counteract each other. So we see that the 5 to the x function is in the middle, and it is in the middle of the log functions over here as well. And then we see that the 10 to the x function, which was the one that was going the fastest over here, is going the slowest over here. It has the slowest growth out of any of the ones that I've listed. I was thinking that I left off my base on this one, but I didn't. It is the common log. It is base 10. So if you were confused as I was for half a second there of where my base was on that one, it's because we're using the common log, because I used the exponential 10 to the x on the other side. So just some things to notice there about the rates of growth between these two families of functions. All right, next we'll take a look at some characteristics of the parent function f of x equals log base b of x, and then we can extend this to any log base whatever, depending on whatever we need to plug in for our base. They all have these same properties. They're all one-to-one functions. We can see, well, first of all, they're functions. Oh, let me switch to a color that works a little bit better on white. We can see they're all functions. They pass the vertical line test. And we can see that they're all one-to-one because they also pass the horizontal line test. So one-to-one functions, that means that they have inverses. We've already been talking about that, so that is good to know. It has a vertical asymptote at x equals 0, so remember that the domain is all positive numbers, which means that we will never get to 0. I'm not hitting 0 very well on that one, but there we go. It's just getting asymptotically close. So that asymptote will also shift around, at least horizontally, as we shift these graphs around. The domain, as we pointed out before, is all positive numbers, and the range is all real numbers. So we looked at that before, and we'll use that again and again as we look here. The x-intercept is always at the point 1, 0. Just like the exponential function always goes through the point 0, 1, and this is its inverse. We'll always get this point 1, 0, and then we also get this other key point, which is also whatever the base is, we'll have a function value of 1. So over here we see it kind of living where it lives, on the right-hand side of 1. Over here it's on the left-hand side of 1, and we can see that those graphs kind of look flipped upside down because essentially they are. The y-intercept, there is none. Because there is a vertical asymptote at x equals 0, that means there is no y-intercept. Unless we start shifting this thing around. If we start shifting it around, then it might have a y-intercept, but the parent function does not. If the base is bigger than 1, we've got this increasing function over here. And if the base is still positive, the base always needs to be positive, but if it's some fractional value between 0 and 1, then we get this decreasing behavior over here like this. So just some general things about, some general knowledge, general facts, characteristics about the parent function here, log base b of x. All right, we'll take a look at sketching a quick graph here by first just sketching the parent function, and then we'll take a look at the new domain range and any new asymptotes that happen to pop up here. So the parent function, we'll just call it p of x, is going to be log base 2 of x. And then it looks like we've got a horizontal shift and a vertical shift, so we will deal with those in our next step here. But for now, I just want to graph this function. We know from the previous page here that there's always going to be a point at 1, 0 rather, at 1, 0. And there will be another point at whatever the base is, which in this case it's 2. Let me scoot this over. I already regret writing that there. There'll be another point here at whatever the base is, which in this case is 2, and then a function value of 1. And then my other one is here at 1, 0. All right, so the parent function is going to look something like that. So here is my log base 2 of x function. And we have a vertical asymptote, as we mentioned before, right here at the line x equal, let me write it below, at the line x equals 0. So now we're going to shift this function 3 units to the left and then 2 units up. So I'm going to maybe change color when I do this. So we'll shift it 3 units to the left and then 2 units up. So just focusing on each point here, we'll start with the one at 1, 0, and we'll go over 1, 2, 3. There's -2, and then we'll go up 3 units. 1, 2, 3, and then we'll go up 2 units. 1, 2. So there's 2. So that is where the first point shifted. And then the other point will get shifted 1, 2, 3 units to the left, and then 1, 2 units up. And then our vertical asymptote is also going to get shifted 1, 2, 3 units to the left. Now there's no real point in shifting a vertical line up, because something that already extends forever in a vertical direction, if it gets shifted in a vertical direction, doesn't change anything. It still hits every point that it was already hitting. But now we know that our graph will look something more like this, where this is the point -2, 2, and this will be the point -1, 3. So there is our transform function there. If we want to take a look at the domain, well, everything got shifted to the left 3 units, so there's some intuition that we can use there as well. But we can also just see from the picture of the graph here, we have a horizontal asymptote at x equals -3. Everything to the right of that is being hit by the graph, so the domain here is from -3 to positive infinity. We're not including -3 because there's an asymptote there. We're never going to attain that value. And then the range, which was -infinity to positive infinity, is still -infinity to positive infinity. If things just got shifted up, we're still just hitting all of the values here. So the range does not change, but the domain does. So there we have it. Oh, and I need to label my my new vertical asymptote there. So there we go. We've got the new graph, and we've got the domain and range. All right, we'll do a little bit more work here talking about the domain of log functions. We're often asked to find them, and then we've got another one here where we'll find the domain, and then we'll look for the inverse of this function as well. Recall that the argument, the input of any of these log functions needs to be bigger than 0. So what I'm saying here is that the input of this function, the argument, needs to be bigger than 0. Well, let's focus on that. What this is saying is that -6x minus 6 must be bigger than 0. If it's not, we can't plug it into the log function. So now we can just solve for x. We'll add 6 to both sides, and we'll get -6x is bigger than 6. We'll divide both sides by -6, and we'll get that x must be bigger than -1. So this tells me that the domain is going to be the interval from -1 to positive infinity. All right, taking a look at this next example here, kind of an interesting looking one. We've got g of x is equal to log base 3 of log base 5 of x. So we've kind of got this logs on logs situation here. So we're going to use the things that we already talked about and we already know about finding the domains of logs. So we'll start by looking at the most inside thing that we're plugging in here, which is just this x that we're plugging into the log base 5 function. And we know that x will need to be bigger than 0. So this tells us that at least we're looking at a domain of 0 to positive infinity, which is not too surprising. That is the domain for the base parent function here. Okay, so now let's take a look at what else is being plugged into a log function. And what's being plugged into the log base 3 function is the log base 5 of x. So what I'm underlining in green now is what is being plugged in to the log base 3 function. So that is telling us that log base 5 of x will have to be bigger than 0. And if we go ahead and rewrite this and put this in the other form, this tells us that x will have to be bigger than 5 to the 0. There's some other ways that we can think about that step there. If that seemed a little too hand-wavy, we'll talk about those in the next video. But this says that x needs to be bigger than 1. Remember, anything to the 0 power is always just 1. So this gives us a bit more of a restriction here. This says that we're looking at a domain of 1 to positive infinity. And we're trying to find the domain of functions being composed with themselves here. We always look at the intersection. So if I take a look at the intersection of these two, we actually just end up getting the 1 to positive infinity because that was the most restrictive of all of the domains that we saw anyhow. So there it is. There's the domain for this kind of weird looking function from 1 to positive infinity. Now we're being asked to find its inverse. So maybe let me make a little bit of space here. I have a feeling that I might want it. Whoops. Oh, come on. There we go. All right, so we're going to find its inverse the same way that we always find inverses. And that's first by writing y equals log base 3 of log base 5 of x. And then we're going to switch the variables. So we're going to write x equals log base 3 of log base 5 of y. And now we're going to solve for y. So what we are going to do at this step is raise both sides. We're going to exponentiate both sides with base 3. And I'm doing that because what we have here on the outside is this log base 3. And so what we're essentially going to be doing, and I'm going to try and make this kind of visually convince you here, is we're making both sides exponents on a base of 3. So maybe I could even rewrite my equal sign down here to make it a little bit clearer, and I'll get rid of that one. What this now says is that 3 to the x is equal to 3 to the log base 3 of log base 5 of y. And why that's nice is that, whoops, I didn't mean to erase that. Why that's nice is 3 raised to the log base 3 of whatever just gives you the inside here. These are two inverse functions undoing each other. So in our next step, we have 3 to the x is equal to log base 5 of y. That is the result of raising a base to a log of the same base. They're just undoing each other, and you just get the input back from that point. So we can do the same thing here. Let me scoot my line over a little bit. We're going to do the same thing now because now we have our y trapped in this log base 5 function. So we'll go ahead and raise both sides to we'll put a base 5 on both sides so that both the sides of the equation we started with become the new exponents. And if I wanted to be more convincing in the way that this looks, I could move my equal sign down a little bit. We'll erase that one. We'll erase that one. And now I have these undoing each other. I have 5 to a log base 5 of something. So when I get out the other side, I'm going to have 5 to the 3 to the x is equal to just y. And now we have it. We've solved for y. That means I can go ahead and rewrite this as this is a g function. G inverse of x. G inverse of x is equal to 5 to the 3 to the x. So there we go. We've got the inverse of this function as well. So there we go. All right, from there it is time to practice. So if you have any questions on the homework, please let me know, and I will see you in our next video.